Welcome to our quantum deep dive.
Hello.
Today, we're plunging into something truly fascinating, technology that could literally redraw the lines of, well, everything.
Sounds exciting.
It is. We're taking a deep dive into quantum lithography.
A key enabling technology for the future, potentially.
Exactly. And we're exploring it through an insightful essay by Jorgo Schneeppert titled Quantum Lithography, Precision für die Nanotechnology.
A good source. Schneeppert covers the core ideas well.
Our mission today, to really unpack this essay, pull out the key insights, and understand why this tech is generating so much buzz.
And why it's so important for, well, the future of nanotechnology.
Right. So maybe let's start with the basics. What exactly is lithography in the first place?
Sure. I mean, fundamentally, it's the bedrock of modern tech, isn't it?
In a way, yeah.
It's how we create all those incredibly fine, intricate structures on surfaces. Think microchips, nanostructured materials.
Like etching tiny pattern.
Exactly. Like incredibly precise stencil work. But at the nanoscale, it's foundational.
And traditionally, we've used classical methods. Light, electron beams.
That's right. Optical lithography, using light through a mask, is the workhorse for chips. Electron beam lithography gives finer detail, but it's slower.
But these methods are hitting walls, aren't they, as we try to shrink things down even further?
Absolutely hitting walls. Physical walls. The main one, especially for optical methods, is the diffraction limit.
The wavelength problem.
Precisely. Physics dictates you just can't focus light down to a spot smaller than roughly half its wavelength. The essay mentions the formula, d equals lambda over 2 sin theta, or the practical version, d equals k alkin A.
So the wavelength of the light fundamentally limits the size of the features you can create.
Correct. And we've pushed this hard using shorter and shorter wavelengths, deep UV, now even extreme UV, EUV.
But EUV is incredibly complex and expensive tech, right?
Astronomically so. It's an engineering marvel, but it shows the extreme lengths and costs needed to push classical limits just a little further. We're really straining against fundamental physics now.
So we need something new. A paradigm shift.
Exactly. And that's where quantum lithography comes in. It's not just tweaking the old methods. It's using quantum mechanics itself to sidestep those classical limits.
Okay, so this is the quantum leap part. How does quantum weirdness translate into drawing finer lines? What are the key quantum ideas from the essay?
Well, it starts with the real basics. Wave-particle duality, for instance.
Particles like photons acting as waves, too.
Yep. De Broglie's HPA is HP. Their wave nature is crucial. And then there's the wave function, psi.
Which describes the quantum state.
Right. But importantly, the probability of finding the particle, which dictates our pattern, is the square of the wave function, psi's too. It's probabilistic.
And for a clear pattern, you need those waves to interfere nicely.
Coherence.
You definitely need quantum coherence. The waves have to maintain a stable phase relationship to create predictable interference patterns. That's essential.
But the real game changer, you're saying, is entanglement.
That's the big one, yes. Einstein's spooky action at a distance, where particles are linked, instantaneously correlated no matter the distance.
Exactly. They share a joint wave function. The essay really emphasizes this because entangled particles interfere differently than independent ones. That's the trick to getting resolution beyond the classical limit.
And superposition, being in multiple states at once. Does that play a role?
It does. A quantum system can be in a combination of states. For lithography, this might mean potentially exposing multiple pattern elements simultaneously. Quantum parallelism, boosting efficiency.
What about Heisenberg's uncertain principle? Doesn't that limit precision? XU2.
It's always there, a fundamental limit. You can't know position and momentum perfectly. But quantum lithography doesn't break it. It kind of works with it cleverly, using entanglement.
How so?
By entangling multiple particles, say n photons, you can arrange their collective state to have very low uncertainty in the property you care about for patterning like their relative positions, potentially at the cost of increased uncertainty in another property, like their total momentum. You're essentially squeezing the uncertainty where it matters least for the pattern.
Okay, that makes sense. You manage the fuzziness. So with these principles, especially entanglement, how does a quantum lithography system actually work?
The core technique relies on creating and using pairs or groups of entangled photons.
How do you make those?
A common method mentioned is spontaneous parametric down conversion, SPDC. You shine a laser on a special nonlinear crystal, and one high-energy photon can split into 2 lower-energy ones that are entangled.
And these entangled photons then create an interference pattern.
Yes, but crucially, because they're entangled, the resulting probability distribution, the Prec2 pattern, has finer features than you'd get with classical light of the same wavelength.
Finer how?
This is the breakthrough highlighted in the essay. The resolution, the smallest feature size d, isn't just limited by the wavelength anymore. It also depends on the number n of entangled photons used together.
Okay.
The effective resolution becomes d equals n.
Wait, d equals lambda divided by n.
Exactly.
So if you use 2 entangled photons, Ne2, you effectively have the limiting wavelength.
That's the potential, yes. Double the resolution.
And with 4 entangled photons, Ne4, quadruple the resolution.
That's the theoretical promise of using n-photon entanglement. This n relationship is why quantum lithography is potentially revolutionary. It bypasses the classical O2 limit.
Wow, that's huge. Are there specific techniques for this?
The essay mentions things like noon states. These are specific types of multi-photon entangled states designed to exhibit this n interference behavior. Getting them experimentally is challenging, though.
It sounds incredibly powerful, just using the quantum link between photons to draw finer lines. The essay also mentioned quantum holography. Is that related?
Yeah, it's presented as sort of an extension. Instead of just 2D patterns, it uses entanglement and superposition to potentially record and reconstruct complex, high-fidelity 3D information. Think manufacturing incredibly detailed nanostructures.
Okay, so the potential precision is amazing. Where could we actually use this technology?
Oh, the applications are potentially vast. Obvious starting point. Nanostructures and quantum dots.
Q-dots for displays, solar cells, even quantum computing qubits.
Precisely. QL could allow us to make them and place them with unprecedented accuracy, which is critical for performance, especially for things like qubit arrays.
And the semiconductor industry must be watching closely.
Absolutely. Chip making is lithography, essentially. QL promises structures nearing atomic scale. Imagine chips that are way denser, faster, using less power.
Could it enable totally new devices, too?
Potentially, yes. Things like quantum wires or other exotic nanoscale components that are just impossible to fabricate reliably today.
What about outside electronics?
Biotechnology is a big area mentioned, for example, making ultra-precise nanopore arrays. For DNA sequencing.
Exactly. Tiny holes to thread DNA through for reading. Higher precision means better accuracy, faster reads, higher throughput, maybe even for analyzing proteins or other biomolecules, too.
And optics. Photonics.
Definitely. Manufacturing nanoscale optical components, nanolenses, photonic crystals, tiny waveguides to control light, and also, crucially, building the hardware for quantum communication.
Like quantum routers or switches. For secure communication.
Yes, the components needed for quantum networks and quantum encryption systems. The precision is key there, too.
It sounds almost too good to be true. What are the catches? The essay must talk about challenges, right?
Absolutely. The challenges are significant, both technical and economic.
Like what?
Well, first, just making enough entangled photons, efficiently, reliably, with high quality. That's still a major research problem. SPDC sources are not super efficient.
Okay, so the source is bottleneck number 1, a big one. Then there's maintaining quantum coherence. These entangled states are incredibly fragile. Any interaction with the environment noise, temperature fluctuations can destroy the entanglement, ruining the precision.
Keeping the spookiness alive is hard.
Very hard, especially outside pristine lab conditions. You also need extremely complex and stable optical systems to manipulate these photons, which adds cost and complexity.
And then scaling it up. From lag demo to factory floor.
That's perhaps the biggest hurdle. Integrating this delicate quantum process into the high-volume, relatively harsh environment of a semiconductor fab, that's a monumental engineering challenge. Plus, the initial investment and operating costs would likely be very high, at least initially.
So lots of research still needed.
For sure, improving the photon sources, better coherence control methods, developing robust optical systems, figuring out integration pathways, demonstrating it works reliably at scale, plenty to do.
Given all that, what's the realistic outlook?
The long-term vision is still very compelling, pushing towards even higher resolutions, maybe automating the process, finding new uses in medicine or materials science. The essay paints it as a really key technology for the whole quantum revolution.
Enabling things we can't do now.
Exactly. But it won't happen overnight. It's a long road.
And are there broader implications discussed? Societal, ethical?
The essay touches on them, yeah, staying neutral. Like any powerful tech, there are questions. Will it be accessible globally or widen gaps? What's the impact on jobs if it enables more automation? could ultra-precision be misused?
So the need for discussion and standards.
Right. International cooperation and thoughtful regulation will be important as it develops.
Okay, so let's try to summarize the core message from Jorgo Schneppat's essay. Quantum lithography is.
It's fundamentally a new way to pattern materials, using quantum effects like entanglement and interference.
The key being that it can overcome classical diffraction limits.
Right, thanks to that DN principle, allowing for potentially much higher precision.
Key advantages. That amazing precision, possible gains in efficiency, and applications across electronics, biotech, quantum tech.
Definitely. But balanced against major hurdles. Generating and controlling quantum states, the complexity, the cost, and the huge challenge of scaling it up for industry.
It really feels like a bridge between deep physics and practical engineering.
It absolutely is. It's about harnessing some of the most counterintuitive aspects of reality to build the future, potentially atom by atom.
So here's a final thought for you to ponder. As this research continues, if we do master quantum lithography and gain the ability to craft structures with near-atomic precision, how might that fundamentally reshape our world? Think about the devices you use, the medical tests you might take, even how we communicate. What changes?
A lot to think about there.
Indeed. A huge thank you for joining us on this deep dive today, guided by the work of Jorgo Schneppat.
My pleasure. Thanks for the great discussion.
And goodbye.